12.7 quadric surfaces. We're going to look at these basic 6 second-degree surfaces in a short video. We're going to start with z equals x squared plus y squared. That's an elliptic paraboloid. And we're going to start off at z equals 0 in the xy plane. If you start off at that, we end up with 0 equals x squared plus y squared. The only solution is 0, 0. That's a point right here. And then if we move up to z equals 1, we have 1 equals x squared plus y squared. That's a circular radius 1. You can make a new reference frame here, 1 unit above. We have a circle. The question is, how do these radii increase? Do we have a cone? Do we have a vortex? Do we have a paraboloid? Well, if you look at this in the zy plane, just cover x squared up. Z equals y squared. That's a parabola. And that is what gives us this shape and this shape. And that's an elliptic paraboloid. It's called an elliptic paraboloid. If you vary these coefficients, it will make these ellipses instead of circles. So that's number 1. Number 2 is a saddle. Let's have a look at that. And I'm going to do y squared minus x squared. It's the same shape, just oriented differently. Instead of x squared minus y squared. A little easier to draw based on the way we do our right-handed coordinate system. And first of all, we're going to start in the zy plane. In the zy plane, x equals 0, you get z equals y squared. And so you end up with a parabola. Then what we're going to do is we're going to move down a bit. And let's suppose this is y equals 2. Plug in 2, we get z equals 2 squared minus x squared. And guess what? We have a concave down parabola. Well, if you continue the y-axis this way, that's what we end up with. And same thing down here. And that's why it's called a saddle. Very easy to remember why it's a saddle. When you switch orientation, it goes from concave up to concave down. Plus y squared concave up, minus x squared concave down. This point right here, next chapter, chapter 14, is what's called a saddle point. It's actually a critical point, but if you look at it this way, it looks like a relative minimum. But if you look at it this way, it looks like a relative maximum. So it's what's called a saddle point. It's the point in the saddle. Now let's look at a hyperboloid of one sheet. One differentiating factor here is the saddle is just z, and this one is z squared. The same thing, the elliptic paraboloid is z, but z squared. Z squared gives us a different shape. Had we subtracted 1 up here, this would have just moved this down 1 unit, would have moved it down. But we're subtracting 1 from z squared, that doesn't perform a very simple transformation. And here's how we're going to graph it. Let's start off at z equals 0. Plug in 0. That's a circle. Circle of radius 1. Now let's suppose we do z equals plus or minus 1. Either one gives us the same outcome. Negative 1 squared is 1. So we end up with 1 is x squared plus y squared minus 1. X squared plus y squared equals 2. Guess what? The radius is about 1.4. Here the radius is 1. Then we move up and we have a bigger radius, and we move down and we have a bigger radius. And that gives us the shape. It's a hyperboloid of one sheet. It's one connected surface. When we do this one, you'll understand where the one sheet significance comes from. If we were to graph this in the xy plane, you'd see we have hyperbolas, or in the yz plane, sorry about that. And also the xz plane. We have a bunch of hyperbolas, but it's very difficult to construct the surface using hyperbolas. A lot easier to construct it using these circles that are layered one on top of another. Now number 4. All we did is we changed this negative to a positive. And if we try to do z equals 0, we can think of this as a circle of radius I. Okay, there's actually no solutions. You cannot plug a real ordered pair in here and sum the squares and get negative 1. It's just impossible. So what happens here is there's nothing but space in the middle. If you let z equals plus or minus 1, that's where things begin to happen. And then plug a 1 in here, subtract the 1s, well, I'll expedite things. You end up with a single point 0, 0. So we end up with a point there and a point there. And we can do z equals plus or minus 2. 2 squared is 4, subtract 1, and we get x squared. You can do the arithmetic. And guess what? The radius is about 1.7, square root of 3. So you move up to 2, we end up with a circle. Move down to negative 2, we end up with a circle. And we end up with that. These again are hyperbolas. That's a hyperbola right there. But it's easier to draw out with circles. And that's where the two sheets comes from. Two separate parts. It's a disconnected surface. So, okay, cone. Z squared equals x squared plus y squared. Looks a lot like this, but z is squared. And it looks a lot like these two, but there's no plus 1 or minus 1 on the end. This gives us an elliptic cone. And like before, you can start off at z equals 0. And you end up with this point right here. Plus or minus 1, you have x squared plus y squared equals 1. You can go up, and we have a circle. Go down, we have a circle. And the question is, what does a profile look like? Well, if we look at it in the yz plane, you can let x be 0. And you actually have z equals plus or minus the absolute value of y. You take the square root, and guess what? That's a linear relationship. That's what gives us a cone. If we do z equals square root of x squared plus y squared, that would just be the top half of the cone. And the bottom would be z equals negative square root x squared plus y squared. Okay, one last one. We have an ellipsoid. I just picked a particular ellipsoid, but in a book they'll have a squared, b squared, c squared here, where a is 2, b is 3, c is 4, but I picked a particular one. And that's basically a sphere that we deform. You can deform it by stepping on it, for instance. Let's draw our Cartesian coordinate system. X, Y, Z. And we'll just sketch the top half. You can conceive of what the bottom half looks like. If you let Z equal 0, this term drops out. You end up with x squared over 4 plus y squared over 9 equals 1. That's simply an ellipse. Let's extend our axes here. It's an ellipse. The x-intercepts are plus or minus 2. And the y-intercepts are plus or minus 3. And you end up with something like that. My artistic abilities are a little limited, but you end up with it's an ellipse. Now, we can find the z-intercept by letting x and y be 0. And we end up with z squared over 16 equals 1. And z equals plus or minus 4. So we go up 1, 2, 3, 4. And there's our z-intercept. Well, the simplest way to sketch this is connect the z-intercept with the intercepts in the xy plane, and there we have it, our ellipsoid. We'd end up with a similar shape on the bottom, since z squared, for any xy ordered pair, you have a plus or minus z solution. So, but I'll just leave it at that, so the drawing doesn't get too complicated. Okay, that's the end of part 1. We'll have a second part to this video in just a short time.